From the smartphones in our pockets, to the wiring that keeps our homes bright, and even the engines that drive our cars forward, copper is everywhere. It is one of the most essential metals on Earth, and yet, very few people know exactly how it's pulled from deep within the ground and turned into shiny, pure copper that powers our modern world. Thousands of meters below the Earth's surface lies a vast treasure chest of copper ore. But unlocking that treasure isn't as simple as digging with a shovel. It's a process that requires giant machines, explosive force, precision chemistry, and weeks, sometimes months of transformation before a rock can become one of the world's most useful metals. Today we're taking you inside that journey, from exploration and blasting to crushing, smelting, and refining. This is the mind-blowing story of how copper is mined, processed, and made ready for the world. But before we dive in, don't forget to hit subscribe, tap the notification bell, and give this video a thumbs up. Trust me, you don't want to miss what's coming next. Copper is often called man's first metal. Why? Because it was one of the very first metals ever used by humans, dating back more than 10,000 years. Ancient civilizations like the Egyptians and Mesopotamians discovered that copper wasn't just shiny and beautiful. It was also strong, malleable, and resistant to corrosion. That meant it could be shaped into tools, weapons, jewelry, and even the very first plumbing pipes. Fast forward thousands of years, and copper remains just as important, if not more. Today, copper is the backbone of modern technology. It conducts electricity better than almost any other common metal, making it essential for power lines, motors, electronics, and renewable energy systems like wind turbines and solar panels. Without copper, much of the modern world would literally go dark. In fact, copper demand is skyrocketing. With electric vehicles, green energy, and global electrification, the world now consumes over 20 million tons of copper every single year. And where does all that copper come from? Not from recycling alone, though recycling is hugely important, but mostly from mining deep deposits hidden inside the earth. These deposits aren't pure copper metal. Instead, they're ores, rocks that contain copper minerals like chalcopyrite, bornite, and malachite. Typically, copper ores only contain a small percentage of actual copper, often less than 1%. That means for every ton of copper extracted, miners must move and process hundreds of tons of rock. This is where the journey begins. Locating those deposits, digging massive mines, and then transforming ordinary rock into one of the most valuable metals on Earth. So, how do we actually find copper in the first place? The Earth's crust contains copper scattered almost everywhere, but only certain locations have concentrations high enough to be mined profitably. That's where exploration geology comes in. Geologists begin by surveying landscapes using satellite imagery, mapping rock formations, and analyzing soil chemistry. They look for signs of copper minerals on the surface, greenish stains of malachite, or bluish hints of azurite. But since the richest deposits often lie deep underground, scientists rely on advanced tools like magnetic surveys, seismic studies, and drilling core samples. When drilling, a cylindrical piece of rock is pulled out of the ground, often hundreds of meters deep. Geologists examine these cores to estimate the size, depth, and grade of a copper deposit. If the results are promising, companies spend years and millions of dollars conducting feasibility studies. They ask questions like, how much copper is really here? How much rock must be moved? What's the environmental impact? Can this mine be profitable for decades? Once approved, it's time to dig. And depending on the deposit, miners use two main methods: open pit mining and underground mining. The journey starts at the primary crusher. Here, gigantic rocks, sometimes the size of a refrigerator, are dumped into a machine with steel jaws. These jaws slam together with immense force, reducing boulders into fist-sized chunks. The process doesn't stop there. Secondary and tertiary crushers further reduce the pieces down to gravel-like sizes. Why so small? Because the smaller the particles, the easier it is to free copper minerals from the surrounding rock. After crushing, the ore heads to the grinding mills. Imagine enormous drums, each bigger than a bus, rotating day and night. Inside, steel balls or rods tumble with the crushed ore. As the drum spins, the heavy balls crush the ore into a fine powder. At this stage, it looks less like rock and more like wet sand or even muddy slurry. This fine grinding is crucial because copper minerals are often locked within the tiniest grains of rock. Now comes the ingenious part, separating valuable copper minerals from waste rock. Since copper minerals often have unique surface properties, miners use a method called froth flotation. This step is magical when you think about it. Out of tons of dull gray rock, we've now isolated a small but powerful concentrate brimming with copper minerals. But we're not done yet. The concentrate still contains sulfur and other impurities, so it needs to be transformed into pure, usable metal. At this stage, enormous conveyor belts and pipelines move the copper concentrate to smelters or processing plants. From muddy slurry, the journey is about to leap into the world of fire, heat, and chemistry. After concentration, the copper-rich slurry, now upgraded to about 30% copper, travels to one of the most dramatic stages in metallurgy, smelting and refining. This is where chemistry, heat, and human ingenuity combine to transform dull concentrate into glowing, usable copper metal. The concentrate, still containing sulfur and iron, is dried and fed into huge furnaces. Imagine steel chambers large enough to hold a small house, burning at over 200 degrees Celsius, 200 degrees Fahrenheit. The molten matte is then transferred to another furnace called a converter. Here, air or pure oxygen is blasted through the molten material. The oxygen reacts with the remaining sulfur and iron, driving them out as gas or slag. The result, a product called blister copper, so named because its surface appears blistered with bubbles of escaping gas. This blister copper is about 98 to 99% pure. But 98% isn't good enough for modern technology. Smartphones, electrical wiring, and medical devices demand ultra-pure copper, 99.99% purity. To reach this perfection, blister copper undergoes electrolytic refining. When the process is complete, what emerges are sheets of copper so pure they gleam like mirrors, ready to be rolled, drawn, and manufactured into countless applications. From ore dug deep in the earth, we've now produced one of the world's most essential materials. The copper you see in wires, plumbing, cars, electronics, even renewable energy systems like wind turbines and solar panels, all trace their origins back to this fiery transformation in smelters and refineries. If you've enjoyed this journey into the hidden world beneath our feet, imagine how many more stories the Earth is waiting to tell us. Subscribe to the channel, hit that notification bell, and join me as we uncover more secrets of science, nature, and the incredible materials that shape our modern life. Don't just watch, be part of the adventure. Glass. It's everywhere. In your windows, your wine glasses, your car windshield, and even the phone you're probably holding right now. But here's the question. Have you ever stopped to wonder where glass actually comes from? I mean, is it mined, grown, cooked up in some chemistry lab? What if I told you it all starts with sand? Yep, that fine grainy stuff you shake out of your shoes after a beach trip. Today, we're going behind the scenes to uncover how something so ordinary becomes something so extraordinary, in a high-tech factory where science meets heat, and raw nature becomes sleek, clear, and ready for the world. So let's start at the beginning, with sand. But not just any sand. We're talking high-purity silica sand, the good stuff. Factories get this special sand from carefully selected quarries, and it has to be squeaky clean. No dirt, no weird minerals, no shells. Just fine, pure silica. It's the backbone of glass. But here's the twist. Sand doesn't work alone. It needs a few co-stars. Soda ash helps the sand melt more easily. Limestone makes the final glass stronger and more durable. Cullet, which is just a fancy word for crushed up recycled glass, helps everything melt faster and uses way less energy. All of this gets delivered in bulk, by truck, train, or even ship, and stored in giant silos. Think of it like a massive pantry for a very hot recipe. Now that we've got our ingredients, it's time to mix the perfect batch. Modern factories don't leave this to guesswork. Everything is done by computer, weighing each ingredient to the gram. Think of it like baking, but on a giant industrial scale. And instead of cookies, you're making windows. Conveyor belts carry the sand, soda, limestone, and cullet into a giant blender called a batch mixer. This machine tumbles everything together so that the mixture is perfectly uniform. In some facilities, they even preheat the mix using leftover heat from the furnace. It's like preheating your oven, but also saving energy in the process. Smart, right? Alright, time to crank up the heat. Literally. The mix heads into a glass melting furnace where temperatures reach a blistering 1500 degrees Celsius. That's over 2700 degrees Fahrenheit. Hotter than lava. Seriously. Inside the furnace, the sand and its companions melt into a glowing orange liquid river. Thick, sticky, and mesmerizing. But this isn't instant soup. It takes time. Up to 24 hours of slow, even heat to get that perfect glass consistency. Factories use sensors and cameras to monitor everything, adjusting the heat, checking the flow, and making sure the glass is as smooth as honey and free of bubbles. Because nobody wants lumpy glass. It's like alchemy meets engineering. Now comes the fun part. Depending on what kind of glass you're making, the shaping process looks totally different. Let's look at the big three. Flat glass. For flat glass, the factory uses something called the float process. Here's how it works. The molten glass flows onto a bed of liquid tin. Yes, real molten tin, because glass floats on it like oil on water. The glass spreads out into a smooth, flat sheet as it glides across the tin. It's kind of like watching pancake batter settle, but glowing hot and way more precise. The sheet cools just enough to hold its shape and then rolls forward like a glowing ribbon. Perfectly flat, perfectly smooth. Bottles and jars. If the factory is making bottles or jars, the molten glass is sliced into gobs, like little dollops of honey. These gobs drop into metal molds, then compressed with air or pressure in 2 steps, first shaping the neck, then the full bottle. This process, called blow and blow or press and blow, is shockingly fast. We're talking 600 bottles per minute, flying down the line like magic. Glass fibers. For insulation or fiberglass, the molten glass is drawn through tiny holes, like pasta through a spaghetti maker, creating thin, hair-like threads. It's fast, hot, and incredibly delicate, and the result is strong, light fibers used in everything from walls to boats. Once the glass is shaped, you can't just let it sit out and cool. That's a recipe for cracks and disaster. So it goes into something called a layer. Basically a long, slow-moving oven. Here the glass cools down gradually, in a controlled environment. This process is called annealing, and it relieves internal stresses that could make the glass shatter down the line. Whether it's a giant window or a little olive jar, annealing is key to durability. And this tunnel isn't short. Some layers are over 100 feet long. Now that the glass is cool and stable, it's time for the finishing touches. Flat glass is cut to size using diamond wheels. Yes, real diamonds. It's the only thing hard enough to score the surface cleanly. Then the edges are smoothed and polished for safety. Some sheets are even coated with thin layers of silver or other metals to create mirrors or solar glass. As for bottles, machines check everything: symmetry, thickness, strength. Every bottle, every jar, every panel is inspected by lasers, sensors, and high-speed cameras. Some lines even use AI to detect the tiniest defects. What doesn't pass inspection? Back it goes to the furnace as cullet to try again. Nothing is wasted. Depending on what the glass will be used for, it might get a few more upgrades. Want stronger glass? Enter tempering. Tempered glass is reheated, then cooled super fast with blasts of air. This makes it 4 to 5 times stronger than regular glass. And if it breaks, it shatters into small, blunt pieces. Much safer. Or maybe you want glass that holds together on impact. That's laminated glass, with a clear plastic layer sandwiched between 2 sheets. It's what keeps your windshield from exploding during a fender bender. And then there's smart glass coatings, like low-E layers that reflect heat but let light through. Perfect for keeping your house cool and your AC bill low. Finally, the finished glass is ready to leave the factory, but it has to be packed just right. Flat panels are stacked with soft pads in between. Bottles are grouped into neat packs and wrapped tight. Fiberglass is rolled or boxed depending on use. Robotic arms lift and stack everything onto pallets. Forklifts roll in, trucks roll out. Some of this glass will travel across the state, some will cross oceans. From your local grocery store to downtown skyscrapers in New York or Shanghai, it all started with a grain of sand. Here's the cool part. Glass is infinitely recyclable. You can melt it down and remake it again and again, without losing quality. Modern glass factories are going green in a big way, using more cullet cuts energy use and emissions. Electric furnaces are replacing gas ones. Solar panels, waste heat recovery, and closed-loop water systems are all becoming standard. Some plants even run on 100% renewable electricity, turning the ancient art of glassmaking into a beacon of sustainable innovation. If you enjoyed this deep dive into how ordinary sand becomes the glass all around us, imagine what else we've got coming. We're just getting started. So don't miss out. Hit that subscribe button, give us a thumbs up if you learned something new, and drop a comment telling us what process you want to see next. Beneath the Earth's crust, hidden in ancient volcanic formations, lie some of the most prized treasures known to mankind. Diamonds. For centuries, these shimmering stones have captivated royalty, industries, and investors alike. But their story begins long before they ever reach a jeweler's display. The history of diamond mining stretches back over 2,500 years to ancient India, the first known source of diamonds. These early gems were found in riverbeds and traded along the Silk Road, believed to bring strength, invincibility, and spiritual clarity. By the 18th century, Brazil had become the world's largest supplier, before the discovery of massive deposits in South Africa changed everything. In 1867, a young boy found a shiny stone along the Orange River, a 21-carat diamond that sparked a modern diamond rush. This led to the founding of some of the world's most famous mines, including Kimberley, home to the legendary Big Hole. Today, diamond mining is a high-tech global enterprise. The world's largest mines span across continents, from Jwaneng in Orapa in Botswana, to Mirny in Russia, Venetia in South Africa, and Diavik in Canada. Some operations reach depths of over 1,000 meters, and each year, more than 130 million carats of rough diamonds are produced globally. But how are these tiny crystals of carbon extracted from solid rock? And what does it take to bring them from the Earth's core to the world's most exclusive boutiques? Join us as we journey deep into the heart of modern diamond mining, a world of massive machines, precision science, and sparkling ambition. Geologists use satellite imaging, geophysical surveys, and soil sampling to identify promising sites. Once a potential kimberlite deposit is located, it's drilled and sampled to assess the concentration of diamonds. This process can take years and millions of dollars in investment before a mine is approved. Only a small percentage of kimberlite pipes actually contain diamonds in commercially viable quantities. If one does, the project moves into the development phase. In open-pit operations, huge amounts of overburden, layers of soil and rock, must be removed. The process begins with explosives, followed by massive hydraulic shovels and dump trucks that can carry up to 400 tons of rock at a time.